In this video, I just want to quickly run through the example of lists and verify that lists are a monad. So what are lists? So we have a functor which maps a set to the set of all lists over that set. And we have two maps, eta and mu. And just to remind us, eta of x is a list, which is just the singleton list, and mu of a list of lists, say 1, 2, 3, 4, 5, and one more, 6 maybe, is the list of lists flattened. So just the list which contains the same elements in the same order, but one level of square brackets removed. Okay, so now we need to check that this is indeed a monad. So what do we have to do? So first we have to say list is a functor. So we've done this previously. Just a quick recap. What does this mean? So if you have a function from x to y, then so in Haskell that would be called map f, but in the more mathematical notation we write list f, must be now a function from lists of x to lists of y. And then let's make an example. So if I have a list with an x and a y, then this is mapped to a list with the same number of elements, but f applied pointwise, as we sometimes say. And now we need to also check that this satisfies the laws of being a functor. So we need to show that this preserves identities. Sorry, I should put the f should be the identity here. If list, I want to say that list preserves identity, and list preserves composition of functions. So I'm not saying that we don't have to do these verifications, but they tend to be a bit boring, and it's something you do privately at home. It's not something you really write out in a paper or a video or an article or a book. But it has to be done. So next, what about eta and mu? So if you go back, there are some properties of eta and mu as well. So eta is a natural transformation. Again, this is something that should be checked. And we spent some time studying natural transformations. So we know that a natural transformation is essentially a parametric function, a function that is defined uniformly in all types, and certainly the singleton is such a function, and flattening is also such a function. So again, one should run through the formal definition of a natural transformation and check that these are natural transformations. But again, this is something one should do at home. Okay, so now we come to the more interesting question about whether the equations are satisfied. So what about the equations? So let's remember the equations one by one. So one equation was this one. So we have an eta here, right? And we want to study the relationship between eta and mu here in this case. So we plug in for x list of x. I should use a different letter than x then, but I think you know what I mean, right? So we take eta for an object which is itself lists over x, right? And then we can flatten this list using mu and get a list again. And then the equation is that mu x after eta list of x is the identity. So if you want to write this down in the more one-dimensional algebraic notation, then we would write mu x after eta list x is the identity. And then maybe we should put the subscript here, list x, because it's the identity on list x. But then again, also, I like to drop this index here, just like we do in programming. Okay, so in case we go back to a formal definition of eta mu, and we actually have formal definitions of eta mu in two different ways even, defined inductively as Haskell functions. We can also do proofs by induction, but for this video I just want to do proofs by example. So let's take just a list here, I don't know, 1, 2, 3. And then what does eta do? Right, so eta is applying singleton to all the elements. No, sorry, eta applies singleton to the whole list, right? So eta applies singleton to the list, so what we get here is the singleton applied to the list 1, 2, 3, and then if you flatten this, we said so for list flattening is very simple because we just keep the order of the elements and remove one layer of parentheses. So we get 1, 2, 3 again, and we see that this is indeed also we get when we take the identity in that direction here. So yes, this equation is satisfied. Before I go on, actually, maybe I should say one more thing, that this equation is kind of formally similar to the equation of monoids, which is telling us that if I do a multiplication with an identity, then with a neutral element, then I get the identity. So the eta is like the neutral element, and if I do a multiplication, that's the mu, with the neutral element, then I get x again. And the x here in our example would be the 1, 2, 3. So at the moment, this is just an analogy, but one can find a setup in which a monad is actually a monoid, and then this equation really becomes the ordinary monoid equation. But that's not the topic of this video. Okay, so next equation. So again, it looks similar, right? So we have again the same types, but it's the identity in the other way around. So this time, before it was like eta list if you want, right? And now we take list eta. So we take again the equation which relates eta mu. It's a different equation, so let's just see in what way it is different. So take the same list here, 1, 2, 3, and we map it over here. But this time, so this is map, right? So this applies eta to all elements of the list. So what we do is we take singletons for elements. So you see that this is different from what we had before. But still, if we flatten this, then we keep the order of the elements and we remove one layer of square parentheses. And then, yes, it's still true that this is the same as the list we started with. So this diagram commutes, which is to say that this equation is satisfied. Okay, so now we have one more equation to check. In our analogy, monad as a monoid, this is now, which corresponds to associativity, if you want. And so one way to remember this is that we had to fill in this square here. And there are two ways to fill this in. So I can take m mu and I can take mu m. These are the two ways to match the types. If I only want to have an equation about mu. And so let's see what that should mean. So we first move this down a bit. Let me also say that m here is now really the list functor, but gets a bit long writing list everywhere. So maybe I can write m instead. So and also this notation here with the mu m is kind of convenient because it's symmetric to this one, but it is more in line with the notation we had before. If I put this as a subscript here, so because this is really what is meant here is the natural transformation mu at the object mx. So this mx is a subscript now here. So okay, to make this slightly more readable, let me move this up a bit. So mu sub mx. Okay, so to understand what's happening here, it's the first thing we should do is to make an example. So let's do this. I think that's the list we've seen before. Oh, we need a list of lists now, right? So we have one more level again. So let me create a bit more space here. So now I have lists of lists, and I assemble those in a list again. So now I have an element of list of list of list of x, and x is, say, the integers here. Okay, so now what this is really about here is to understand what's the difference is between flattening at type list of x and what it means to apply the functor m to flattening. So to apply the functor m to flattening, to apply the list functor to a function means to actually apply it to the elements of the list. Should put the subscripts here actually on the muse, in case you were wondering. If it was a lecture in class, you could just give me a shout, but here I have to be more careful. Okay, so what does it mean to apply mu, the flattening, to the elements of the list? I think we know this already. So maybe I just remove the outer parenthesis just for a moment, right? And what I'm thinking about is this arrow which goes down here. So I want to apply the flattening to the elements of the list, and to make this more readable, I remove the outer parenthesis just for a moment. And so what I have to do is I have to flatten this list and I have to flatten this list, right? So we've seen how this works. So I get 1, 2, 3, 4, 5. That's flattening the first list, and then I get 6 from flattening the second list. And now, so all I've done is I applied flattening inside this container, if you want, right? So think of the monad as a container. Then what we are doing is we are applying the function inside the container. And so now I need to kind of wrap it into the container again, right? So now I put the parentheses here, and there, here, and here. So actually, maybe you'll find this helpful. If I do this in a different color, magenta, oops, the outer parenthesis in magenta here, then these are the parentheses which kind of survive when I go down here. And maybe also these parentheses correspond to these m, so it makes sense to draw them in the same color. So this is the magenta m, and the magenta m. Okay, so then let's contrast this with what happens if I go the other way around. So let us look now again at this here, right? So now it's different. Now I'm not flattening inside, but I'm flattening outside. So flattening means removing one level of parentheses, and I'm keeping now the parentheses on the inside, but I'm flattening the two levels on the outside into one level. So maybe one way of doing this is just to, I know that I leave the innermost level intact, right? So I'm not operating here on these lists. But what I'm essentially doing is I'm kind of removing these here. Right, so I'm removing the middle level of parentheses here. And so what I'm ending up with is this list here. And you see that it's different from what we got before. But you also see that if we flatten these two now, we get the same list in the end. Okay, so this is not a formal proof that mu as defined for the list monad satisfies this equation, but you have a formal definition of mu in the Haskell files, an inductive definition, and if you're interested in a little math exercise, you can also try to give a formal inductive proof that this works really for all lists of lists of lists. Thanks for watching.